Right, I'd like to try to, well, basically kind of a modest goal here. Just want to unify all of the forces in nature, the single guiding concept. So the known forces of nature are, first we have the strong force. By the way, this wasn't known about until the last century, so this is part of what we call modern physics. The only forces that were known in, say, the 1900s were the electromagnetic force and the gravitational force. And so the strong force is one of those that has been identified and analyzed over the past century. And so the strong force then holds together atoms. Should say here, well, there are two different forms of the strong force, but the one that I'm looking at here holds atoms together and also holds the nucleus together. So it kind of does double duty here. Okay. So by holding the atoms together, what I mean then is that it is able to overcome the repulsive effects in the nucleus of the electric force of the proton. And these protons are very close together in the nucleus. And so it shouldn't be a surprise that if there were a force that could hold together the nucleus against these positive charges that are smashed together so tightly, that it would have to be very strong, right? Because here we're talking about the distances here being vanishingly small. And so the natural tendency then, just due to electrostatic repulsion, would be for these things to fly apart. But they don't. And so we could imagine that there are like little short-range hooks that can hold together the nucleons, the little elementary particles within the nucleus, against this very, very strong electrostatic force. But it has a weakness. The strong force has a weakness, and its main weakness is that it's only very short range. And this, by the way, is the reason why the nucleus is so small. Because the nucleus can only exist within the range of the strong nuclear force. And so we might wonder then, well, what's the mechanism that allows for this force to act over such a short distance? And by the way, how big is this distance too? Well, so typically, as we saw in an earlier lecture, the size of the nucleus is on the order of femtometers. Which is 10 to the minus 15 meters. So it's essentially then 100,000, typically the size of an atom. So the atomic size then is so much bigger than the nucleus that if you were to compare them, say if you had the nucleus was a baseball at home plate, Dodger Stadium, the outermost electrons would be way outside the stadium. It could be as much as a mile away, with the nucleus on that scale. And so we're dealing then with a nucleus in terms of its size. It's barely there at all. And yet that's where most of the action is taking place in an atom. It's happening with the central force that is exerted by the nucleus, but it's so tiny that it was difficult to even identify that what its nature was. And Rutherford was able to show that with his gold foil experiment. Okay, so how could we get a force like this that can only act over such short distances? And the answer is we have what's called an exchange force. So this is the mechanism. So the idea here then is that we have virtual particles that are created out of nothing. And so these virtual particles are exchanged between nucleons. By nucleons here, I mean particles like the proton and the neutron. But what limits the range, essentially, is the uncertainty principle. So we can say that delta E, delta T, is approximately equal to h bar. And so to borrow enough energy for a virtual particle, the delta E here must have at least the rest energy of a virtual particle. We could call this mc squared, where m is the mass of the virtual particle. And then delta T is the amount of time that you can borrow that energy for before you have to pay it back. In other words, this is a typical lifetime of the virtual particle. Now, how fast can these virtual particles go? Well, the fastest any particle can go typically is the speed of light. So we can say then that the speed of light times delta t is equal to delta x, where delta x is the maximum range of the virtual particle. Okay, and so if we plug in then for delta t here, h bar over delta e, and then rewrite delta E as the mass of the virtual particle times c squared, we get h bar divided by mc squared. Then we get the maximum range of the virtual particle. It's on the order then of c h bar divided by m c squared, right? So that's c times h bar divided by delta E, which is mc squared. Or the range of the virtual particle looks like h bar over mc. Okay, so what this means then is that we are limited in the range by the Planck's constant. Okay, and so if this delta x for a virtual particle that's exchanged by the strong force is such that this is on the order, say, of a few femtometers, on the order of femtometers, then that means that this range is being controlled essentially by Planck's constant and, of course, also by the speed of light. And so we might ask ourselves then, well, what if h bar was equal to 1 instead of 10 to the minus 34 meters? Well, that means that the range of the strong nuclear force would be 10 to the 34th times bigger than it is. And so then delta x would be 10 to the 34 times a femtometer, essentially, something like that. It would be that much bigger if Planck's constant divided by 2 pi were equal to 1. Okay, and so 10 to the 15, 10 to the minus 34, so what we're looking at here is a difference then of 10 to the 19th power meters. Now 10 to the 19th power meters is on the order of light years. Okay, and so that's how big the nucleus of an atom would be. But if everything else were proportional, then that means that the outermost electrons might be close to the size of the visible universe. So we would have a single atom then that would have a size that, just by changing this one constant, that would be, instead of being this tiny little thing that's 1/100,000th times the size of an atom, and barely even there in terms of our ability to measure it, would be an incredibly huge structure. Now, okay, so we produce these virtual particles. How does that give rise to the force? Well, let's just imagine that we're throwing something back and forth. I throw something to this particle. We could imagine that to be a virtual particle. That virtual particle throws something back at me. That would create a repulsive force. Okay, and so if you continue to throw these virtual particles back and forth at each other, you can get a repulsive force in this way. But if you send something around and it follows all possible paths and it ends up taking a boomerang type of a path like this, then throwing it this way, and then assume that somehow it's able to find its way around in this boomerang type of trajectory, that could create an attractive force. And so it turns out that not just the strong force, but also the other forces, which we'll be looking at in this section, including the gravitational force and the electromagnetic force, which we can see summarized up there on the data projector. These are all generated by virtual particles that are being exchanged back and forth. So you go, well, gravitation, we just learned that in gravitation, general relativity, that gravity is kind of an illusion and it's caused by the curvature of space and time. Well, that's true, but this is an equivalent formulation in which we can think of the gravity force as being generated by a graviton. And so this is still theoretical, but we believe that every force can be broken down into essentially an exchange of virtual particles that have different properties. And because these virtual particles have different properties, the forces have different strengths.